So dimensional analysis is a technique that's used a lot in fluid mechanics and also other areas. Basically what you're trying to do is make the problem easier. The way we do that is by getting rid of some of the variables. So the goal of dimensional analysis is to reduce the number of variables in the problem. The full details of what to do is the subject of the next lesson. But to do this, the way we reduce the number of variables is through something called dimensionless numbers. And so that's what this current lesson is devoted to. So to talk about dimensionless numbers, we need to know about dimensions and or units, another way to think about it. So fundamental dimensions, at least in SI units, are mass, length, and time. So in terms of dimensions, we have mass as m in square brackets. So any square brackets means I'm talking about the dimension of mass as opposed to the unit of mass. So dimension of mass, m, dimensions of length, capital L, dimensions of time, capital T, and of course units in the SI system, kilograms of mass, meters for length, S for time, seconds. And so what we can do with these fundamental dimensions is make other dimensions, other variables, such as acceleration, for example. Acceleration is some length over a time squared, so acceleration can have a dimension of L over T squared, and of course SI units, meters per second squared. So dimensionless number, just as its name suggests, is a number where all the dimensions or units completely cancel out, so it's left with 0 units or 0 dimensions. Example of this is something called the force coefficient. Force coefficient is defined to be the force divided by 1/2 velocity squared times area. So if we look at that in terms of its dimensions, force has dimensions of mass, length over time squared. If you have a hard time figuring out what dimensions are, easier thing to do is look at units. So units of force is a Newton. A Newton is the same thing as kilogram meter per second squared. So kilogram meter per second squared is mass, length over time squared. So there's my dimensions of force. Density, mass over length cubed. Velocity, length over time. And area, length squared. And so we look at the dimensions of this force coefficient CF. In terms of dimensions, force is mass, length over time squared. 1/2 is dimensionless, so no dimensions for the 1/2. Density, mass over length cubed. Velocity, length over time, whole thing squared. And then area, length squared. Then you can see we have a mass on the top, mass on the bottom, so those guys are going to cancel out. I have a 1 over time squared on the top, 1 over time squared here on the bottom, so those guys are going to cancel out. And then I have a L squared here, an L squared there, and 1 over L cubed there. So essentially I end up with extra L on the bottom. This is L to the 4th over L cubed, so an extra L. Fill out this L on top. No dimensions left, just a 1. So that is in fact a dimensionless number.
So this table shows the common variables in fluid mechanics along with their dimension. So any length, diameter is going to have a dimension of length, obviously. Area is going to have length squared. Volume will be length cubed. Velocity will be length over time. Acceleration, length over time squared. Density, mass over length cubed. Viscosity, mass over length time. Pressure, mass over length time squared. Shear stress, same as pressure, mass over length time squared. Force, mass length over time squared. And then surface tension, mass over time squared. And then this table shows the common combinations of variables giving us common dimensionless numbers, such as the Reynolds number, density, velocity, length over viscosity. The coefficient of pressure, Cp, is pressure divided by 1/2 rho v squared. Coefficient of force, saw that in the example at force over 1/2 rho v squared L squared. Mach number is a velocity divided by the speed of sound. Crude number of velocity divided by square root of acceleration due to gravity times a length, which is usually a height. Then the Weber number, density, velocity squared, length over surface tension. So anytime viscosity is an important parameter in the problem, the Reynolds number becomes an important dimensionless number for that. Similarly, if there's a pressure, you're generally going to end up with a coefficient of pressure, Cp. If there's a force, coefficient of force shows up. If compressibility is an issue, that's when the Mach number comes into play. Fluid number, generally free surface flows. If you have flow over a spillway or gravity pulling fluid down a certain height, that's where the fluid number comes in. And then Weber number if there's any surface tension effects.